There's a number that astronomers have been quietly refining for the better part of 2 decades, and it is enormous. It represents the estimated count of planets in our galaxy alone where liquid water could theoretically pool on a surface. Current best estimates place that figure somewhere in the tens of billions for the Milky Way, and when extended across the observable universe, the number climbs into quintillions. That is not a rounding error or an optimistic guess. It is the careful product of statistical inference from real detection data. And sitting beside that enormous figure is a second number, one that has not changed in all of recorded human history. The second number is the count of worlds where life has been directly confirmed to exist. That number is exactly 1. The one world we know to be inhabited is the one we are standing on tonight. What lives between those two figures, the billions of plausible homes and the single confirmed address, is the question this catalog is built around. We're going to walk through it slowly, and we're going to take our time. The confirmed exoplanet count, the running tally of planets around other stars that astronomers have formally verified, has now passed roughly 6,000. That number would have seemed like science fiction to anyone working in planetary science before 1995. The candidate count, planets detected but not yet formally confirmed, runs several times higher than that. Inside that larger population, a quieter and more specific subset has emerged over the years of careful observation. These are the worlds that sit inside what researchers call the habitable zone, the orbital band around a star where temperatures could allow liquid water to persist on a rocky surface. A smaller subset still are both small enough and dense enough to be considered genuinely rocky rather than gaseous. From those filtered numbers, the field has been attempting the patient and somewhat unsettling work of estimating how many worlds anywhere in any direction might right now be capable of supporting life. The answer that keeps coming back from the data is a great many. The galaxy does not appear to be stingy with the conditions life requires. Current estimates suggest that somewhere between 30 and 80% of Sun-like stars host at least one Earth-sized planet in their habitable zones. Applied to the roughly 400 billion stars of the Milky Way, that range produces an estimate in the tens of billions for plausibly habitable worlds in our galaxy alone. Extended to the observable universe, with its hundreds of billions of galaxies, the figure becomes a number that no longer functions as a number in any meaningful human sense. It becomes a way of saying, everywhere you look, the conditions are probably being met somewhere. What is striking about this is not just the scale, but the consistency. Different research teams using different methods keep arriving at the same basic order of magnitude. The galaxy is not a barren place with a few lucky exceptions scattered across it. It appears to be, by the most straightforward reading of the available evidence, dense with possibility. That is the headline answer, and it is real, and it is also only the beginning of the question. Because a world that could support life and a world that actually does are two very different things. Holding that distinction carefully is what tonight is about. There are 2 layers to the question, and they operate at very different scales. The first layer is the catalog of named worlds, specific planets identified by name, host star, orbital distance, and enough physical characterization to think of them as places rather than data points. That layer is the more tractable of the 2. It contains a few dozen serious entries, each with a small fact sheet attached. There is Kepler 22b, sitting roughly 620 light-years away, the first habitable zone planet ever confirmed around a star meaningfully similar to our Sun. There is Proxima Centauri b, just 4¼ light-years out, orbiting the closest star to us. There is the TRAPPIST-1 system, with its 7 Earth-sized rocky worlds arranged in resonance around a dim, ultra-cool dwarf less than 40 light-years away, 3 of them sitting inside the habitable zone. There is K2-18b, a subneptune world 124 light-years distant, with a hydrogen atmosphere and possible ocean and the faint chemical fingerprints of something interesting in its skies. Each of these is a real place with a real story, and we will spend time with each of them. The second layer of the question is the population problem, and it is considerably harder. How many such worlds exist across the Milky Way as a whole? And how many across the broader universe? Answering that requires extrapolating from the small, instrument-biased sample of detections we have actually made to the vastly larger population that current telescopes cannot yet see. The biases are significant. Transit surveys favor close-in planets around small stars. Radial velocity surveys favor massive planets near bright sun-like stars, and the habitable zone rocky worlds we most want to find are often the hardest to detect. Astronomers are not counting habitable worlds directly. They are counting the ones that happen to fall into the narrow geometry their instruments can reach, and then doing the statistical correction to infer the rest. That correction is where most of the uncertainty lives. The range of estimates it produces is wide, but even the conservative end of that range yields numbers that are difficult to hold in the mind. The galaxy almost certainly contains billions of plausible homes. The universe almost certainly contains more than any language was built to describe. Before the catalog itself begins, one distinction deserves to be stated plainly and held carefully throughout. A habitable world is a world where life, as we know it could in principle survive, where the temperature range, the presence of water, and the basic physical architecture fall within the parameters that Earth life requires. An inhabited world is one where life is actually present. The first question can be partially answered by observation. The second requires either a detected biosignature in a planet's atmosphere or, eventually, a probe. These two questions are often quietly blurred together in popular coverage of exoplanet discoveries, and that blurring does real damage to the clarity of the picture. When a press release announces a new Earth-like world, what has been found is almost always a world that meets the temperature and size criteria, not a world where life has been detected. The distinction matters enormously because the count of worlds meeting the first criterion is in the billions, while the count of worlds meeting the second remains, for now, exactly 1. We will hold those two numbers apart from each other all the way through. The toolkit that built the catalog is worth understanding before we walk through it. 4 detection methods are doing most of the work. The transit method watches for the small, periodic dimming of a star's light when a planet passes in front of it from our line of sight. A Jupiter-sized world produces about a 1% dip, while an Earth-sized world produces a dip of roughly 1/10,000th. The radial velocity method measures the tiny Doppler shift in a star's spectrum caused by the gravitational tug of an orbiting planet pulling the star into a small mutual orbit. Jupiter pulls our sun at about 13 meters per second. Earth pulls it at about 9 centimeters per second, and modern instruments are approaching the sensitivity needed to measure shifts that small. Direct imaging physically separates a planet's light from its host star's glare. Currently feasible only for large, young, widely separated worlds, but approaching viability for Earth analogs with the next generation of space observatories. Gravitational microlensing catches chance alignments where a foreground star briefly amplifies background starlight, with a planet around the foreground star, leaving a characteristic signature in that brightening curve. Each method has its own blind spots, and together they have produced a catalog that is real but heavily shaped by what each instrument happens to be good at finding. The working definition of habitability used most often in the field is this: a world is habitable if, given an Earth-like atmosphere and reasonable surface pressure, liquid water could persist on its surface across geologically long timescales. That definition is doing several quiet jobs simultaneously. It uses liquid water as a proxy for the conditions that Earth life requires, because liquid water is the medium in which Earth's biochemistry operates, and the solvent without which no known life can function. It requires surface presence rather than deep subsurface presence, which is the more conservative of the available options. And it requires geological persistence, not a brief warm moment during a favorable orbital phase, but stable liquid water across millions or billions of years. This is the conservative definition, and it is the one most commonly used when the headline numbers are generated. It is not the only definition in use, and later in the catalog we will return to several broader versions that expand the count in their own ways. For now, the conservative definition is the frame, and even within it, the estimated population of qualifying worlds is vast. The catalog's named entries represent something genuinely new in the history of science. For most of human history, the question of whether other worlds existed around other stars was purely philosophical. There was no observational foothold, no data, no way to distinguish one answer from another. The first confirmed exoplanet around a main sequence star arrived in 1995, and the count has been accelerating ever since. The subset of those planets sitting in habitable zones around stars that could plausibly support life has grown from 0 to several dozen confirmed and candidate entries in roughly 2 decades. Each new entry in the catalog is a named place, not a hypothesis, not a thought experiment, but a real world tracing a real orbit around a real star somewhere in the galaxy tonight. The fact that we can now speak about habitable exoplanets as a catalog of specific places rather than as a statistical abstraction is one of the more quietly remarkable developments in the history of astronomy. It means the question has changed character. It is no longer purely a question about numbers. It is beginning to be a question about particular addresses. Settle in, then, as the catalog opens. There is no urgency here, and no need to carry anything forward from the day. The question we're sitting with is one of the largest questions modern science has ever had the instruments to begin answering, and it rewards patience more than speed. Over the next several hours, we will walk slowly through the named worlds, the ones that have earned a place in the catalog, the ones that carry the most promise, and the ones that have already begun to give partial answers back. We will hold the numbers honestly, including the ones that are still uncertain. We will hold the silence honestly too, because the silence is part of the picture. And we will let the question stay open where it remains open, because the honest answer is still being assembled, observation by observation, world by world, year by year. The galaxy is large. The catalog is real. Let the night settle around you, and let's begin. The word habitable is doing more work than it first appears, and that work deserves a careful unpacking. It is not simply a synonym for pleasant or survivable or even Earth-like in any loose sense. The field uses it in a specific, constrained, and deliberately conservative way that shapes every number downstream. Understanding what the phrase actually means and what it quietly excludes is the necessary foundation before any named world can be evaluated honestly. The habitable zone is defined as the orbital band around a star where a rocky planet, given reasonable atmospheric conditions, could maintain liquid water on its surface across geological time. That definition sounds simple, but each of its clauses is doing real work. Geological time means billions of years, not a warm season or a favorable orbital phase. Reasonable atmospheric conditions means Earth-like in pressure and composition, not any possible atmosphere. Liquid water on the surface means exposed, not buried beneath kilometers of ice or locked in a subsurface ocean. The definition is conservative by design, because conservative definitions produce the most defensible numbers. Even so, the numbers it produces are enormous. The inner boundary of the conservative habitable zone is set by a process called the runaway greenhouse limit. As a planet receives more stellar energy, water vapor increases in its atmosphere, and water vapor is itself a powerful heat-trapping gas. More vapor traps more heat, which evaporates more water, which adds more vapor to the cycle. At a critical threshold, the feedback becomes self-reinforcing and unstable, and the oceans boil away entirely into the atmosphere. Ultraviolet radiation from the host star then breaks the water molecules apart, and hydrogen escapes to space, leaving a dry and airless surface behind. The outer boundary is set by a different mechanism, called the maximum greenhouse limit. As a planet moves farther from its star, more carbon dioxide is needed in the atmosphere to keep the surface warm enough for liquid water. At some point, the carbon dioxide itself begins to condense as ice, collapsing the greenhouse effect and sending the planet into a permanent freeze. For our own sun, the conservative zone runs from roughly 0, 95 AU at the inner edge to roughly 1, 37 AU at the outer edge. Earth at 1 AU sits comfortably near the middle, which is not a coincidence. It is the baseline the definition was built around. Venus and Mars are the canonical demonstrations of what happens at each extreme. Venus at 0.72 AU sits well inside the inner edge of the conservative zone and represents the runaway greenhouse outcome made fully real. Its surface temperature is high enough to melt lead, its atmosphere is roughly 90 times denser than Earth's, and its water inventory dissociated and escaped to space long ago. Malshotin. 52 AU sits just outside the outer edge and tells a different story, one of past habitability rather than present failure. The Martian surface carries clear geological evidence of ancient rivers, lakes, and possibly shallow seas, suggesting the planet once sat inside some version of the habitable zone before its atmosphere thinned and its surface froze. Of the 3 rocky planets in our solar system's temperate band, 1 succeeded and 2 did not, which is a small but instructive sample size. The solar system has effectively run the habitability experiment 3 times in the same orbital neighborhood, and the outcome was not uniformly positive. That is worth holding in mind before applying the zone definition to worlds around other stars. The optimistic habitable zone is a wider version of the same boundary, defined not by theoretical limits, but by the empirical record of past liquid water on Venus and Mars. If Venus hosted surface oceans for perhaps 100 million years before its runaway greenhouse fully engaged, then the inner edge of habitability may sit closer to the star than the strict runaway threshold implies. If Mars maintained rivers and lakes for hundreds of millions of years before atmospheric collapse, the outer edge may extend farther than the maximum greenhouse model predicts. For our Sun, the optimistic zone runs from roughly 0.75 AU to roughly 1.77 AU, nearly twice the width of the conservative version. Most of the headlines that announce new Earth-like worlds are using the optimistic zone, while most of the peer-reviewed population estimates use the conservative one. The choice between them changes the inferred number of habitable worlds in the galaxy by roughly a factor of 2. Neither version is wrong. They are answering slightly different versions of the same question, and the honest reading holds both simultaneously. The habitable zone shifts its position depending entirely on the luminosity of the star at its center. Around a small, cool red dwarf, the zone sits much closer in, sometimes at orbital distances less than 1/10 of an AU, with orbital periods measured in days rather than years. Around a large, hot star of the F or spectral class, the zone sits farther out, with orbital periods measured in years. The same temperature window that Earth occupies at 1 AU from the Sun can exist at radically different distances depending on how much energy the central star is producing. This scaling has a significant practical consequence for the catalog. Most of the habitable zone candidates detected so far orbit M-type red dwarfs, because those close-in orbits are geometrically favorable for transit detection and produce stronger radial velocity signals. The red dwarf habitable zone is easier to observe, which is why it dominates the catalog, but easier to observe does not automatically mean more likely to be inhabited. The question of whether M-dwarf habitable zone planets are genuinely comparable to Earth is one of the most actively contested issues in the field. The phrase that needs to be held clearly before the catalog begins is this: the habitable zone is a temperature window and nothing more. Being inside, it is a necessary condition for surface liquid water, but it is very far from a sufficient one. A planet inside the habitable zone can still be uninhabitable for any number of independent reasons, each of which operates entirely separately from orbital distance. It can lack an atmosphere, or have one too thin to hold heat, or one so thick that it greenhouses the surface past the runaway threshold. It can be tidally locked, with one hemisphere in permanent daylight and the other in permanent darkness. It can be stripped to bare rock by repeated stellar flares over billions of years. It can lack a magnetic field to deflect the stellar wind from eroding its atmosphere. It can lack plate tectonics, removing the carbon cycle that acts as a long-term climate thermostat. It can be the wrong size, too small to retain gases or too large to remain rocky. The habitable zone is the address on the envelope. It tells you where to look but whether anything is inside the envelope depends entirely on what is in the letter. Magnetic fields are one of the most consequential of these additional conditions. Earth's magnetic field is generated by the slow circulation of liquid iron in its outer core, and that field deflects the stream of charged particles flowing outward from the sun before they can erode the upper atmosphere. Without it, the solar wind would have stripped Earth's atmosphere away across geological time, much as it did on Mars. Mars once had a magnetic field generated by its own molten interior, but roughly 4 billion years ago the core cooled and the dynamo shut down. The field faded, the solar wind began its slow work on the Martian atmosphere, and over the following billion years the greenhouse effect collapsed, the surface water froze, and the planet became what it is today. Whether a planet maintains a long-lived magnetic field depends on whether its interior stays hot and molten long enough to sustain the dynamo, which in turn depends on size, composition, and tidal environment. Of the rocky worlds in our own solar system's habitable zone, only Earth currently has one. That is not a minor detail. It is one of the central reasons the planet remained habitable long enough for us to be here asking the question. Plate tectonics function as a planetary thermostat on Earth, and their absence may be one of the most underappreciated habitability conditions in the catalog. The slow movement of crustal plates over billions of years drives a carbon cycle that regulates atmospheric carbon dioxide across geological timescales. When the climate warms, rainfall increases, weathering reactions pull carbon dioxide out of the air, and ocean sediments lock it away. When the climate cools, volcanic outgassing replenishes the atmospheric carbon dioxide, and the greenhouse effect rebuilds. This feedback loop has kept Earth's surface temperature within the habitable range despite the sun brightening by roughly 30% since the planet formed. Without plate tectonics, the carbon cycle does not close, the thermostat is missing, and the climate has no long-term stabilizing mechanism. Venus almost certainly lacks plate tectonics. Mars almost certainly does, and Earth has them for reasons that are still not fully understood. Probably some combination of size, water content, and early thermal history. Whether plate tectonics are common on rocky worlds elsewhere in the galaxy is a genuinely open question, and the answer will matter enormously for the inhabited fraction of the habitable catalog. A large stabilizing moon and a quiet host star round out the most critical architectural conditions. Earth's moon, unusually large relative to its host planet, exerts a gravitational torque that has kept Earth's axial tilt stable near 23.5 degrees for billions of years. Without it, that tilt could wander between extreme values over tens of millions of years, producing climate swings far more violent than anything Earth's biosphere has actually experienced. The moon itself formed from the debris of an early collision with a Mars-sized body, a low-probability event that most rocky planets in the galaxy probably did not experience. Host star activity adds another layer of conditional probability. G-type stars like our Sun are relatively quiet. K-type stars, slightly smaller and cooler, are quieter still. Many M-type red dwarfs are the opposite, producing frequent superflares that can deliver hundreds or thousands of times more ultraviolet and X-ray radiation than the strongest solar events. Ross 128, Teegarden star, and TRAPPIST-1 are among the M dwarfs considered comparatively quiet, which is precisely why their planets receive more serious habitability consideration than planets around more active hosts. The galactic location of the host system adds one final layer. The Sun sits roughly 8 kiloparsecs from the galactic center, inside a thin annular band where metallicity is high enough for rocky planet formation and the supernova rate is low enough for biospheres to persist, a region estimated to contain perhaps 20 to 30% of the Milky Way's total stellar population. Every press release announcing a new habitable zone world is reporting the temperature window and the temperature window alone. The magnetic field status is almost certainly unknown. The tectonic history is unknown. The atmospheric composition is unknown. The stellar activity record across billions of years is unknown. The moon inventory is unknown. The galactic position has been checked, but the other conditions remain entirely open. A confirmed habitable zone world is a real and meaningful detection. It is the first filter past the necessary condition established, the address on the envelope confirmed. But the letter is still sealed. Whether each of these worlds has the full architectural stack that Earth assembled, the field, the tectonics, the moon, the quiet star, the right galactic neighborhood, the persistence across billions of years, is the question that the name catalog is only beginning to approach. With the zone defined and the conditions laid out, the specific worlds that have earned a place in that catalog can finally be examined one by one, starting with the planet that opened the door. The conservative definition, then, is the floor, and the floor turns out to be considerably higher than most people expect. But the building has more stories than the ground level suggests, and climbing them changes the count in ways that matter enormously. The question of where liquid water can exist in the universe is not the same question as where liquid water can exist on a sunlit rocky surface at comfortable pressure. Those are related questions, but they are not identical, and the gap between them is where most of the galaxy's habitable volume actually lives. Once you allow the definition to stretch even slightly beyond the surface water on a rocky world model, the numbers begin to grow in ways that the conservative estimate does not capture. The stretch is not speculative indulgence. It is grounded in direct observation of our own solar system, which turns out to be a much wetter place than its habitable zone would suggest. The relevant evidence is sitting in the outer solar system, cold and dark, and largely ignored by the headline figures. It has been there the whole time, quietly revising the answer upward. Europa is the most instructive single example, and it has been known for decades without fully reshaping the popular framing. This moon of Jupiter, the smallest of the 4 large Galilean satellites, carries a global ocean of liquid water beneath an ice shell estimated somewhere between 10 and 30 kilometers thick. The ocean is not warmed by sunlight. Europa sits far outside any conventional habitable zone, receiving a tiny fraction of the solar energy that reaches Earth. What keeps the water liquid is tidal heating, the continuous gravitational kneading that Jupiter's enormous mass applies to Europa's interior as the moon traces its slightly elliptical orbit. The ocean beneath the ice is in contact with a rocky seafloor, and at that interface, hydrothermal vents may be generating the kind of chemical disequilibrium that powers entire ecosystems around Earth's mid-ocean ridges. The water is real, the heat source is real, and the chemistry is plausible, none of which has anything to do with orbital distance from the Sun. Enceladus, one of Saturn's smaller moons, makes the case even more directly because its ocean is not merely inferred but sampled. Cryovolcanic plumes erupting from the moon's south pole vent material directly into space, and the Cassini spacecraft flew through those plumes and analyzed their contents. The results were striking. Water, salts, simple organic compounds, and molecular hydrogen, the last of which is a known energy source for microbial life around Earth's hydrothermal systems. An ocean is leaking into space and telling us what it contains, and what it contains is not inconsistent with the conditions that support life on Earth. Ganymede and Callisto, the 2 larger outer Galilean moons, also appear to harbor subsurface oceans based on magnetic field measurements and gravitational modeling. Titan carries both surface hydrocarbon lakes and a deep subsurface water ocean of its own. Triton, Pluto, and several of the larger Kuiper Belt objects may have subsurface liquid water as well, maintained by residual internal heat and radioactive decay across billions of years. When you add up all the liquid water in the outer solar system, the hidden oceans of Europa, Enceladus, Ganymede, Callisto, Titan, and the probable subsurface reservoirs beyond, the total volume exceeds the liquid water on Earth's surface by an estimated factor of more than 30. The most water-rich environments in our solar system are not in the habitable zone. They are in the cold, outer reaches, past the snow line, sealed beneath ice in the dark, orbiting gas giants that the conservative definition never considered. This is not a minor footnote to the habitability story. It is a fundamental revision of where the story is actually set. The solar system's liquid water budget is dominated by environments that no surface temperature calculation would ever find. If that pattern holds across the galaxy, and there is no obvious reason it should not, then the conservative count of habitable worlds is not just an underestimate, it is measuring the wrong thing. Extended to the galaxy as a whole, the subsurface ocean picture changes the population estimate in a direction that is difficult to fully quantify, but clearly significant. Any rocky moon in tidal contact with a sufficiently massive planet can maintain a subsurface ocean at almost any orbital distance from its host star. The tidal heating mechanism does not care whether the system is inside or outside the conventional habitable zone. It cares only about orbital geometry and the masses involved. A free-floating rogue planet, ejected from its original system during the chaotic early period of planet formation and now drifting through interstellar space with no star at all, can maintain a subsurface ocean driven entirely by its own internal heat, sustained by primordial warmth and radioactive decay for billions of years. Some recent calculations suggest that the total habitable volume in the galaxy, measured by the presence of liquid water in any accessible form, exceeds the habitable volume defined by surface water on rocky planets by many orders of magnitude. The galaxy may not primarily be a place of warm, sunlit Earths. It may be a place of cold, dark worlds with hidden oceans sealed beneath ice, turning slowly in the absence of any light at all. The Hycean class represents a different kind of stretch, one that operates at the planetary rather than the moon scale. The term combines hydrogen and ocean to describe a proposed category of worlds sitting between Earth and Neptune in size, roughly 1 to 3 Earth radii, with a thick hydrogen-rich atmosphere and a global liquid water ocean beneath it. The class is hypothesized rather than confirmed, but the logic is physically coherent. A hydrogen envelope acts as a powerful insulating layer, trapping heat far more efficiently than a thin nitrogen-oxygen atmosphere. And an ocean beneath that envelope can remain liquid across a much wider range of orbital distances than the conservative habitable zone would ever predict. A Hycean world could be habitable at distances where a rocky Earth analog would freeze solid, because the greenhouse effect of a thick hydrogen atmosphere is not the same as the greenhouse effect of a thin one. If the class is real and common, it roughly doubles the population of potentially habitable worlds in the galaxy by extending the effective habitable zone outward into orbital territory the conservative definition excludes entirely. Tidally locked worlds around red dwarfs were once dismissed from habitability consideration almost automatically on the reasonable-sounding grounds that one hemisphere bakes and the other freezes. More recent climate modeling has softened that dismissal considerably. A tidally locked planet with even a modest atmosphere will transport heat from its permanent day side to its permanent night side through atmospheric circulation. And the boundary between those two hemispheres, the terminator, the ring of perpetual twilight, can maintain moderate temperatures across its entire circumference. Cloud feedback at the substellar point, where the star hangs motionless directly overhead, may further stabilize the day side by reflecting enough stellar energy to prevent runaway heating. The terminator zone of a tidally locked world is not identical to Earth's surface environment, but is not obviously incompatible with life either. A narrow band of dim, reddish, permanent dusk circling the planet like a ring, where temperatures might stay within the range that Earth organisms tolerate. Whether that ring is actually habitable depends on the atmosphere, and whether the atmosphere survived the host star's early activity is the question that determines everything else. Subglacial habitability adds yet another layer to the count, one that Earth itself demonstrates directly. Lake Vostok, buried beneath nearly 4 kilometers of Antarctic ice, hosts a microbial community that has been sealed from the surface for millions of years, drawing energy not from sunlight, but from the slow chemical exchange between the surrounding rock and the ice ceiling above. The community is sparse and slow metabolizing, but it is alive, and it is alive in conditions that no surface temperature calculation would identify as habitable. extended to the galaxy. This means that even a planet sitting well outside every version of the habitable zone, frozen solid, atmospherically stripped, orbiting a dying star, could still host microbial life at the rock-ice interface if its interior retains enough geothermal heat to maintain a thin liquid layer. The habitable volume expands again, this time in a territory that is not just outside the conservative zone, but outside the optimistic zone as well. The rogue planet population adds the most dramatic revision of all to the headline count. The Milky Way contains an estimated several hundred billion rogue planets, worlds formed either without a host star or ejected from their original systems during the gravitational chaos of early planetary formation. Recent microlensing surveys suggest that rogue planets may actually outnumber stars by a factor of several, making them the most common type of world in the galaxy by raw count. Most of them are probably small and cold all the way through. But the larger ones, rogue super-Earths and rogue Neptune-mass worlds, can in principle retain enough internal heat from primordial radioactive decay to sustain subsurface liquid water for billions of years, entirely independent of any star. A rogue world with a thick hydrogen atmosphere drifting through interstellar space, lit by nothing, orbiting nothing, could maintain a habitable ocean beneath its surface almost indefinitely. The galaxy may contain more habitable rogue worlds than habitable star-attended worlds, and the conservative count misses every single one of them. No confirmed exomoon has yet been detected, despite serious observational effort, because the detection sits at the very edge of current instrumental capability. But the population is almost certainly real and almost certainly large. The solar system has more potentially habitable moons than potentially habitable planets. And by analogy, the galaxy almost certainly contains a vast population of large moons orbiting giant planets inside or near the habitable zones of their host stars. A first confirmed habitable exomoon would shift the count significantly and demonstrate that the moon-based habitability pathway operates beyond our own system. These 6 stretches taken together, subsurface oceans, Hycean worlds, terminator zones, subglacial environments, rogue planets, and exomoons, expand the question of habitability from a narrow temperature window around a sunlit star to something much broader and much harder to fully enumerate. The conservative catalog of named habitable zone worlds, which we are about to walk through one by one, represents the floor of this count, not the ceiling. The galaxy has many ways to keep water liquid, and we are only now beginning to appreciate how many of those ways do not show up in the headline figure at all. The catalog of named worlds begins not with the nearest candidate or the most Earth-like, but with the first. Kepler 22b sits roughly 620 light-years from Earth in the direction of the Cygnus constellation, orbiting a star that belongs to the same broad G-type class as our own Sun. That host star, designated Kepler 22, runs about 300 degrees cooler at its surface than the Sun does, with a radius approximately 97% of the Sun's and a luminosity around 79% as bright. In every meaningful sense, it is a slightly smaller, slightly cooler, slightly older version of the star we orbit, and that resemblance is precisely what made the discovery feel significant. The planet itself completes one full orbit every 290 Earth days, tracing a path at roughly 0.85 astronomical units from its host. Because the star is dimmer than the Sun, that closer distance still places the planet inside the conservative habitable zone, near its inner edge. Its equilibrium temperature, without any atmospheric warming, works out to approximately 260 Kelvin, or about -12 degrees Celsius. With an Earth-like atmosphere layered above it, the surface temperature would climb towards something resembling a mild terrestrial afternoon. The confirmation of Kepler 22b, announced in late 2011 from Kepler Space Telescope data, was the moment the modern habitable exoplanet era stopped being theoretical and became a catalog of specific addresses. What the confirmation established was the proof of concept, and what it left open was almost everything else that actually matters. The planet's radius is approximately 2.4 times Earth's, which places it in a transitional range, where rocky super-Earths and volatile-rich mini-Neptunes overlap and cannot be distinguished by size alone, without a direct mass measurement. The interior composition remains genuinely undetermined. It could be a heavy rocky world with surface gravity roughly twice Earth's, or a deep global ocean with no exposed land at all, or a hydrogen-wrapped gas body with no solid surface beneath the clouds. The most commonly favored interpretation among researchers who have studied it is the ocean world scenario, based partly on density arguments and partly on elimination. A purely rocky composition at that radius would require unusually high density, and a thick hydrogen envelope seems less likely at the lower end of the mini-Neptune size range. If the ocean world reading is correct, the surface beneath the water has never been seen and almost certainly never will be. The ocean itself would run tens or perhaps hundreds of kilometers deep, topped by an atmosphere whose composition remains entirely unknown to us. There would be no continents, no shorelines, no exposed rock of any kind, just water extending from horizon to horizon under an overcast sky we cannot yet describe. The enthusiasm that followed the announcement was real, and the numbers attached to it were not fabricated, even if they were not formal scientific estimates. Individual researchers, speaking in interviews rather than in published papers, placed the probability of life on Kepler 22b as high as 95 to 99% in the weeks after confirmation. That framing expressed something genuine, which was that the discovery of a habitable zone planet around a sun-like star so early in the search was not what the field had predicted. The expectation had been that such planets would be rare, difficult to find, and far between. They turn out to be neither rare nor difficult to find in any fundamental sense, and the enthusiasm was the field absorbing that surprise in real time. The proper framing now, roughly 15 years later, is considerably more measured. We do not know whether Kepler 22b is rocky, oceanic, or gaseous, and that single uncertainty cascades through every downstream question. We do not know whether it has an atmosphere or what that atmosphere contains. We do not know whether its rotation is synchronized with its orbit or whether it experiences day-night cycles at all. The planet sits in the habitable zone. That is established, and it matters, but almost everything else about it remains genuinely open. For years after Kepler 22b, the same instrument produced a second announcement that drew comparable public attention. The planet Kepler 452b was announced in mid-2015 as the first near-Earth-sized world found in the habitable zone of a star closely resembling our Sun, and the press coverage quickly settled on the phrase, Earth's older cousin. The phrase carried because it was accurate in a specific and meaningful way. The host star, Kepler 452, has a surface temperature within 20 degrees of the Sun's and sits at an estimated age of around 6 billion years, roughly 1.5 billion years older than our own star. The planet orbits at approximately 1.05 astronomical units, nearly identical to Earth's distance from the Sun, with an orbital period of 385 Earth days, within 5% of an Earth year. Its radius is about 1.6 Earth radii, large enough to be plausibly rocky, and its estimated mass runs to approximately 5 Earth masses, implying surface gravity roughly twice what we experience here. The equilibrium temperature, given Earth-like reflectivity and atmosphere, will be broadly comparable to Earth's. By the conservative criteria the field uses, Kepler 452b is a habitable world, and the age of its host system is the detail that makes it genuinely striking. A billion years is not an abstract quantity when you're thinking about the history of life. On Earth, a billion years is the difference between a planet of single-celled microbes and a planet of organisms complex enough to look back at the sky and ask what else is out there. If life arose on Kepler 452b at any plausible early date in the system's history, it has had more time to evolve than Earth's entire biosphere has accumulated. That is not a rhetorical flourish. It is a straightforward consequence of the system's age, and it is one of the reasons the announcement drew the response it did. The complication is that Kepler 452b's position near the inner edge of its host star's habitable zone has been slowly degrading as that star brightens across its main sequence lifetime. Stars of this type brighten by roughly 10% per billion years, and the inner edge of the habitable zone migrates outward as a result. Some climate modeling suggests the planet may already be entering the early stages of a runaway greenhouse, transitioning toward the Venus outcome from the inside of the zone rather than from outside it. A second complication arrived in 2018, when a follow-up statistical analysis raised the possibility that the original transit signal was a false positive produced by stellar noise rather than a real planetary transit. The planet's confirmed status still stands in the mainstream catalog, but the confidence level is lower than the original press release implied. And the honest reading is that Kepler 452b is a compelling candidate whose reality is not yet fully secured. Kepler 186f, announced in 2014, hold a different kind of distinction in the catalog. It was the first planet within 10% of Earth's radius ever found in the habitable zone of any star, which made it the first genuinely Earth-sized habitable zone world rather than a super-Earth approximation. The host star, Kepler 186, is a small M-dwarf sitting roughly 580 light-years away, and the planet's orbital period of 129 Earth days reflects that close-in geometry. Its equilibrium temperature without atmospheric warming works out to approximately 180 Kelvin, or about -93 degrees Celsius. Cold enough that liquid water on the surface would require a substantial greenhouse effect to maintain. With a thick enough atmosphere, the surface could warm into habitable conditions. Without one, it would remain frozen. The M-dwarf caveats apply here, as they do to most of the catalog's entries. The planet is almost certainly tidally locked. The host star has a history of flare activity, and the atmospheric status is entirely unknown. But by the strict size criterion, Kepler 186f was the first Earth-sized habitable zone world in the catalog, and that distinction is real regardless of the uncertainties that follow it. Kepler 1649c, confirmed in 2020 from a reanalysis of archival Kepler data, sits even closer to Earth in both size and estimated temperature, with a radius of about 1.06 Earth radii and a stellar flux roughly 75% of what Earth receives. One of the highest Earth similarity index scores in the entire confirmed catalog. The catalog's nearest entry is also its most tantalizing, for reasons that have nothing to do with size or temperature and everything to do with distance. Proxima Centauri b sits 24 light-years from Earth, orbiting the closest star to the solar system, and its confirmation in late 2016 via radial velocity measurements established it as the nearest known exoplanet of any kind. The host star, Proxima Centauri, is the faintest of the 3 stars in the Alpha Centauri system, an M-type red dwarf with a mass about 1/8 of the Sun's and a luminosity roughly 17 thousandths of the Sun's, too dim to see with the unaided eye despite being our nearest stellar neighbor. The planet orbits at approximately 0.049 astronomical units. Closer to its star than Mercury is to the Sun by a factor of 8, but because the star is so dim, that distance places the planet near the middle of the habitable zone by temperature. Its minimum mass is 1.07 Earth masses, with an expected true mass around 1.3 to 1.4 Earth masses after statistical correction for unknown orbital inclination. The equilibrium temperature without an atmosphere runs to approximately 234 Kelvin, or about -40 degrees Celsius. With a substantial atmosphere, the surface could warm into the liquid water range. By the simplest available reading, Proxima b is a roughly Earth-mass rocky planet in the habitable zone of the nearest star to us, and that sentence is one of the more remarkable things modern astronomy has produced. The complications that follow that simple reading are significant, and they deserve to be held honestly alongside the optimism. At 0.049 astronomical units from its host, Proxima b has almost certainly been tidally locked across the system's 4 billion-year history, with one hemisphere in permanent daylight and the other in permanent darkness. Without an atmosphere to circulate heat between the two sides, the day side would overheat and the night side would freeze any volatile solid. With an atmosphere, a moderate temperature terminator ring could form and persist, but whether the planet has retained any meaningful atmosphere is the central open question. Proxima Centauri is a flare-active star, producing frequent outbursts of ultraviolet and X-ray radiation that can spike to hundreds or thousands of times the equivalent flux Earth receives during strong solar events. Repeated across billions of years, that bombardment is capable of stripping an unprotected atmosphere entirely. Some modeling suggests the atmosphere is long gone, leaving bare rock exposed to the full flare environment. Other modeling, more optimistic, suggests that a strong magnetic field and a large initial volatile inventory could have preserved habitable conditions in the terminator zone despite the flares. The honest current position is that Proxima b represents the floor of the optimism spectrum, the nearest known potentially habitable world, which may in fact be uninhabitable, and which the next generation of extremely large ground-based telescopes should be able to characterize atmospherically within the next 10 to 15 years. Proxima Centauri is now known to host at least 2 additional planet candidates alongside its habitable zone world. Proxima Centauri c, announced in 2020, is a candidate super-Earth of approximately 7 Earth masses at roughly 1.5 astronomical units. Well outside the habitable zone in the cold outer reaches of the system, its existence considered probable but not yet fully confirmed. Proxima Centauri d, announced in 2022, is a small inner candidate of perhaps 1/4 Earth mass, orbiting inside Proxima b's orbit on a roughly 5-day period. Not habitable, but instructive about how densely packed M-dwarf systems can be. The larger Alpha Centauri binary, just slightly farther away, offers a different kind of promise. Alpha Centauri A is 8G2V star essentially identical to the Sun in temperature, with only a slightly larger radius. Alpha Centauri B is AK1V star, slightly smaller and cooler. The pair orbit each other over an 80-year period, with their separation ranging from about 11 to 36 astronomical units, wide enough to allow stable planetary orbits in each star's habitable zone. In 2024, a candidate planet from a James Webb Space Telescope direct imaging program around Alpha Centauri A was reported, with an inferred orbital distance placing it roughly in the habitable zone. The detection is preliminary and unconfirmed, but if it holds, it would represent the nearest fully habitable Earth analog around a Sun-like star yet identified. The broader neighborhood within a few dozen light-years of the Sun contains several additional named candidates worth holding in mind as the catalog continues to grow. Ross 128b, 11 light-years away, is a rocky planet of approximately 1.35 Earth masses orbiting an M-dwarf that is unusually quiet by the standards of its spectral class, with low flare activity that substantially improves the planet's habitability prospects relative to most M-dwarf candidates in the catalog. Teegarden star B and C, at 12.5 light-years, are Earth mass candidates with some of the highest Earth similarity index scores in the entire known catalog, orbiting an old and comparatively quiet M-dwarf, whose stability makes them worth continued attention. Wolf 359c at 14 light-years is a super-Earth of approximately 4 Earth masses on the inner edge of its host's habitable zone. Gliese 667cc at 23 light-years is a super-Earth of roughly 3.8 Earth masses firmly inside the habitable zone of an M-dwarf that is itself part of a triple stellar system. Tau Ceti, a G8V star at 12 light-years that has long attracted habitability speculation for its Sun-like character and proximity, has candidate super-Earths in or near its habitable zone, though the radial velocity signals remain contested. Within 50 light-years of Earth, the statistical expectation from Kepler data suggests dozens of habitable zone rocky planets are waiting to be detected, most of them still hidden below current instrumental thresholds, and the nearest fully confirmed Earth analog around a Sun-like star may be closer than any entry currently in the catalog, simply waiting for the instruments that can find it. The TRAPPIST, One system sits 39.5 light-years from Earth, and its strangeness begins with the star. TRAPPIST-1 is an M8V ultra-cool dwarf, sitting at the absolute lower boundary of what qualifies as a true hydrogen-burning star. Its mass is approximately 0.089 solar masses. Its radius about 0.121 solar radii, making it only marginally larger than Jupiter. The surface burns at roughly 2,500 Kelvin, the color of a dim coal rather than anything resembling sunlight. Its luminosity is approximately 0.05% of the Sun's, a figure so small it barely registers against the background of stellar populations. Despite being a star, it produces so little light that standing on any of its planets, you would see a dark red ember hanging in a perpetually dim sky. Its estimated age is approximately 7.6 billion years, more than 3 billion years older than our own Sun. And because M-dwarfs of this size burn hydrogen so slowly and so efficiently, TRAPPIST-1 will remain on the main sequence for hundreds of billions of years. Every Sun-like star in a galaxy will have long since exhausted itself before this one even approaches middle age. The system it hosts is, in a quiet way, one of the most architecturally remarkable things the catalog contains. 7 confirmed Earth-sized rocky planets orbit this dim red ember, and they do so in a configuration that is not random. The orbital periods form a resonant chain, with each consecutive planet's period relating to its neighbors in near-integer ratios that have held the architecture stable across billions of years. Planet B completes an orbit in 1. 5 Earth days, C in 2. For days, D in 4 days, E in 6. 1 days, F in 9. 2 days, G in 12. 4 days, and H in 19 days. The gravitational coordination that produces this pattern is called a resonance chain, and it is the same mechanism that locks Io, Europa, and Ganymede around Jupiter, scaled up to planetary distances. The entire 7-planet system fits inside an orbital radius smaller than Mercury's distance from the Sun. From the surface of any one of these worlds, the neighboring planets would appear as visible disks in the sky, some large enough to show surface features at closest approach. At the nearest conjunction between planets E and F, an observer on either world would see the other as a disk roughly twice the apparent size of our Moon, with features potentially resolvable to the naked eye. The resonance that keeps the system stable also keeps the planets close enough to be, in a literal visual sense, each other's permanent companions in the sky. The 7 planets range in radius from approximately 0.77 Earth radii at the smallest to approximately 1.13 Earth radii at the largest, with none significantly departing from Earth size in either direction. Their bulk densities, estimated from the combination of radius and mass measurements, are broadly consistent with rocky compositions, though the outer planets may carry a modest volatile fraction. The 3 habitable zone worlds are planets E, F, and G, and of these, TRAPPIST-1 stands out in a way that no other confirmed exoplanet in the entire catalog can match. Its radius is approximately 0.92 Earth radii, its mass approximately 0.69 Earth masses, and its orbital period of 6.1 days places it firmly inside the habitable zone of its host star. Its Earth Similarity Index sits at approximately 0.95, the highest score of any confirmed exoplanet yet detected by any method. By every available metric of physical comparison, TRAPPIST-1e is the most Earth-like world currently known to exist. TRAPPIST-1f, with a radius of approximately 1.04 Earth radii and an orbital period of 9.2 days, sits near the center of the habitable zone. TRAPPIST-1g, with a radius of approximately 1.13 Earth radii and an orbital period of 12.4 days, sits near the outer edge. All 3 carry Earth Similarity Index scores among the highest in the confirmed catalog, and all 3 have been priority targets for atmospheric characterization since the James Webb Space Telescope became operational. The early results from that characterization effort have introduced a note of caution that the field is still processing. JWST observations of the two innermost planets, TRAPPIST 1b and C, have now been analyzed, and the findings are not encouraging in the way early optimism had anticipated. The dayside thermal emission measurements for both planets are consistent with bare rocky surfaces sitting in direct radiative equilibrium with the stellar flux, without the heat redistribution signature that a thick atmosphere would produce. There is no detectable atmospheric blanket transporting warmth from the lit hemisphere to the dark one, and no evidence of a substantial gaseous envelope of any kind. The most straightforward interpretation is that both inner planets are essentially naked rock, baked by their host star in the manner of Mercury, stripped of whatever volatiles they may once have carried. The implications for the habitable zone planets E, F, and G are indirect but not irrelevant. If the two innermost worlds have lost their atmospheres entirely across the system's 6 billion year history, the question of whether the outer habitable zone planets fared better is genuinely open rather than comfortably assumed. Atmospheric stripping from stellar wind and flare activity diminishes with orbital distance, but the system is old enough that even the outer planets have faced billions of years of exposure. The first direct atmospheric measurements of the habitable zone TRAPPIST worlds are now being analyzed, and the results will substantially reshape the field's expectations for M-dwarf habitability at the population level. Whatever those results eventually show, the system retains a quality that no atmospheric measurement can diminish. TRAPPIST 1 will still be burning hydrogen long after every G-type star in the galaxy has exhausted its fuel and cooled to a white dwarf remnant. If life exists anywhere in the system, in any subsurface environment, at any hydrothermal interface, beneath any ice-covered ocean floor, it has access to a time horizon that no other known planetary system can offer. The question of habitability for TRAPPIST 1 is therefore not only a question about current conditions, but about the extraordinary duration across which conditions could in principle persist. Even a biosphere that is currently marginal, clinging to existence in a thin terminator ring or a sealed subsurface environment, would have trillions of years ahead of it to develop, adapt, and potentially complexify in ways that no Earth analog world around a sun-like star could match. The system is, in this sense, less a snapshot than a long-duration experiment still in its early chapters. The catalog can hold it as both a cautionary data point and a genuinely open question, neither dismissed by the early atmospheric results nor uncritically celebrated as a confirmed habitable system. It is the place where M-dwarf habitability is being tested most rigorously, and the answer it gives will shape how the field thinks about the most common type of star in a galaxy for decades to come. 124 light-years from Earth, in the direction of the constellation Leo, a different kind of world is tracing a 33-day orbit around a small red star, and is the most discussed planet in the catalog for reasons that have nothing to do with its size or its distance. K2-18b orbits an M2, 5e red dwarf with a mass of approximately 0.45 solar masses and a luminosity of roughly 2% of the Sun's. The planet itself has a mass of approximately 8.6 Earth masses and a radius of approximately 2.6 Earth radii, placing it firmly in the sub-Neptune category. Too large to be purely rocky, too small to be a true gas giant with a thick hydrogen envelope dominating its structure. Its orbital semi-major axis is approximately 0.143 astronomical units, and its equilibrium temperature, without any atmospheric contribution, works out to approximately 255 Kelvin, or about -18 degrees Celsius. With a substantial atmosphere layered above it, the surface or ocean temperature could climb considerably higher. The planet belongs to a proposed class called Hycean worlds, a name combining hydrogen and ocean, in which a thick hydrogen-rich atmosphere sits above a global liquid water ocean, extending the effective habitable range well beyond what conservative rocky world calculations would allow. The class is not yet confirmed as a real and populated category, but K2-18b is the best current candidate for membership in it, and the reasons for that assessment have been building since 2023. In that year, an analysis of James Webb Space Telescope observations of K2-18b's atmosphere reported the detection of both methane and carbon dioxide in the planet's spectral signature, alongside a notable absence of ammonia. That combination is precisely what the Hycean model predicts: a hydrogen-dominated atmosphere above a liquid water ocean, with chemical processes at the ocean surface consuming ammonia and generating methane as a byproduct. A pure mini-Neptune with a deep hydrogen envelope and no underlying ocean would not produce this particular chemical fingerprint. The atmospheric chemistry is not conclusive proof of the Hycean configuration, but it is a strong consistency check, the kind of result that makes the hypothesis harder to dismiss and more worth pursuing with follow-up observations. The same analysis also reported a tentative detection of dimethyl sulfide, a small organic molecule that on Earth is produced almost exclusively by marine microorganisms, particularly phytoplankton living in the sunlit upper layers of the ocean. The significance of that tentative detection is difficult to overstate in terms of what it would mean if confirmed. Dimethyl sulfide has no known abiotic production pathway that generates it in the quantities suggested by the spectral feature, and its presence in the atmosphere of an ocean world would be extraordinarily difficult to explain without invoking some form of biological activity. The detection is faint, sitting at low statistical confidence, and the results from follow-up observations have been mixed. Some analyses strengthening the case for the molecule's presence, others attributing the spectral feature to methane variations or instrumental artifacts. The question is not settled, and the honest framing is that K2-18b currently holds the most suggestive biosignature observations in the history of exoplanet science, held at arm's length by the uncertainty that still surrounds them. Several other worlds have been proposed as candidate members of the Hycean class, and their growing number suggests the category may be real and populated rather than a theoretical curiosity built around a single ambiguous example. TOI 1452b, approximately 100 light-years from Earth, is a super-Earth of about 1.7 Earth radii in the habitable zone of an M-dwarf host, with bulk density measurements suggesting a substantial water component that is consistent with the Hycean model. LHS 1140b, 49 light-years away, is another super-Earth in the habitable zone of an M-dwarf, and recent JWST observations have produced preliminary suggestions of a hydrogen-rich atmosphere above a possible ocean, though the characterization remains early and tentative. Kepler 138d, at 218 light-years, is an ocean world candidate based on density measurements, not strictly inside the habitable zone, but useful as a comparison case for understanding how water-rich subneptunes behave. There are now perhaps a dozen named candidates for the Hycean class distributed across the broader catalog, none confirmed as habitable, but several showing atmospheric chemistry consistent with the model's predictions. If the class is real and common, it has substantial implications for the population estimate, because subneptune-sized planets with hydrogen atmospheres are considerably easier to characterize spectroscopically than rocky Earth analog worlds, and their effective habitable zone extends significantly farther from the host star than the conservative surface water calculation would ever reach. The first confirmed biosignature on any exoplanet may arrive not from a rocky world resembling Earth, but from a hydrogen-wrapped ocean planet that the conservative definition would never have flagged as a candidate at all. Beyond the headline systems, the broader catalog of confirmed and candidate habitable zone world has grown to several dozen named entries, most of them known only from basic transit parameters or radial velocity signatures, each of them nonetheless a real specific world somewhere in the galaxy. Gliese 581g, claimed in 2010 at approximately 20 light-years, was one of the earliest habitable zone candidates. Though its status remains uncertain, some analyses support the radial velocity signal. Others attribute it to stellar activity rather than a planetary companion. Gliese 832c, 16 light-years away, is a confirmed super-Earth of approximately 5 Earth masses in the habitable zone of an M-dwarf host. with an orbital period of roughly 36 days and the standard tidal locking caveats that accompany most M-dwarf candidates. Kepler 442b, at approximately 1,190 light-years, is a confirmed habitable zone super-Earth of about 1.3 Earth radii around a K-type star, with an orbital period near 240 days and an Earth similarity index of approximately 0.83. One of the highest scores in the Kepler catalog for a world orbiting a star that is not an M-dwarf. Kepler 438b, at 470 light-years, is a confirmed habitable zone super-Earth of about 1 Earth radii around an M-dwarf, with an orbital period of roughly 35 days and a host star active enough that some analyses have raised concerns about atmospheric stripping over the system's history. Barnard's star, the second closest stellar system at 6 light-years, is an old and exceptionally quiet M-dwarf whose habitability prospects are among the best in the immediate stellar neighborhood, though the candidate planet announced in 2018 at its outer habitable zone edge has since been disputed and its existence remains uncertain. Lalani 2-1185, the fourth closest star at 8.3 light-years, hosts a tentative candidate of perhaps 3 Earth masses near the inner edge of its habitable zone, tidally locked, but orbiting a star quiet enough to make the atmospheric retention question worth asking seriously. The catalog continues to grow every month, with new entries arriving from test survey data, from reanalyses of archival Kepler observations, and from ground-based radial velocity programs pushing toward ever finer precision. TOI 700d, at 101 light-years, is a small habitable zone planet of approximately 1 Earth radius around an M-dwarf, one of the most precisely characterized rocky habitable zone worlds in the TESS catalog. TOI 2285b, at 42 light-years, is a candidate habitable zone planet around a K-dwarf, which means a quieter host star and better atmospheric retention prospects than most M-dwarf entries carry. The Kepler catalog alone contains roughly 50 named planets that meet at least the basic criteria for habitable zone candidacy, most of them around M-dwarfs with the familiar caveats. A smaller fraction around K-dwarfs and G-dwarfs, with a stellar environment is calmer and the case for long-term atmospheric persistence is stronger. Each entry in this growing inventory is a real place, tracing its own orbit around its own star tonight, while the catalog that records it continues to be updated. The sheer accumulation of names is itself the point. Not because each one is a confirmed habitable world, but because each one represents a location in the galaxy where the first necessary condition has been met, where the address on the envelope has been confirmed, and where the question of what is inside the letter remains entirely open. The population statistics built from this catalog suggest that within 50 light-years of Earth alone, dozens of habitable zone rocky planets should exist around M-dwarfs and several around K and G-dwarfs, most of them not yet detected, because current instruments are still approaching the sensitivity required to find them. The name catalog we have walked through tonight is the floor of what the galaxy contains, and the next decade of observations is expected to raise that floor substantially, bringing dozens of currently invisible worlds out of the statistical estimate and into the catalog of specific named places, each one a new address, each one a new sealed letter, waiting for the instruments that can finally read what is written inside. The number that organizes everything else in this conversation is called Eta Earth, written with the Greek letter ETA. It represents the average count of Earth-sized habitable zone planets per sun-like star across the galaxy. Current best estimates from multiple independent research teams cluster between approximately 0.3 and 0.8. A NASA analysis published in 2021, drawing on the complete Kepler dataset, places the value at approximately 0.5 for sun-like stars specifically. The conservative interpretation pushes that figure down towards 0.1, meaning roughly 1 in 10 sun-like stars host such a world. The optimistic interpretation pushes it towards 0.8, meaning 4 out of every 5 sun-like stars qualifies. The honest current range spans that entire territory, and both endpoints remain scientifically defensible. Multiplying even the conservative figure by the Milky Way's roughly 40 billion sun-like stars produces numbers in the billions. The broader definition, including quieter M-dwarfs and K-type stars alongside strict sun analogs, yields estimates in the hundreds of billions. The galaxy, by every available reading of this single statistic, is not a sparse place. The commonly cited headline figure of approximately 40 billion Earth-sized habitable zone planets in a Milky Way represents the conservative midpoint of these calculations. It is not a precise measurement. It is a working order of magnitude built from statistical inference and instrumental correction. The honest range runs from perhaps 2 billion at the most pessimistic end to perhaps 100 billion at the most optimistic. Applied to the observable universe, which JWST Deep Field Surveys now estimate contains between 200 billion and 2 trillion galaxies, the figures climb past any number that functions meaningfully in human experience. Estimates for Earth-similar habitable zone worlds across the observable universe range between 10 to the 18th and 10 to the 22nd power. Between 1 quintillion and 10 sextillion is the current working answer to the cosmic version of the question. The Milky Way is a relatively large galaxy, so the per-galaxy average elsewhere is probably somewhat lower than our local figure. The order of magnitude, however, is settled in the affirmative regardless of which end of the range you accept. The universe contains habitable worlds in quantities that no language built for human-scale experience was ever designed to hold. The Drake equation is the formal structure that organizes this multiplication into a single coherent chain of reasoning. It expresses the number of currently communicating technological civilizations in the galaxy as a product of 7 sequential factors. The rate of star formation in the Milky Way is well measured and contributes a known quantity to the chain. The fraction of stars that host planets is now known to be essentially 1, based on a decade of Kepler and test survey data. The average number of habitable zone planets per such star, Eta Earth, has been narrowed to the range between 0, 1 and 0, 8 discussed above. The remaining 4 factors, the fraction of habitable worlds where life arises, where intelligence develops, where communicative technology emerges, and how long such civilizations persist, remain unknown by many orders of magnitude each. The first half of the Drake equation has been substantially answered by 2 decades of exoplanet science. The second half remains as open as it was when Frank Drake first wrote the equation down in 1961. The known terms tell us the galaxy is full of places where life could begin. The unknown terms leave entirely open whether it ever does, and whether having begun it ever becomes anything detectable from across interstellar distances. The gap between what we now know and what we still do not is the exact size of the question this catalog was built around. The conditional probability chain that connects habitable to inhabited runs through at least 4 distinct bottlenecks, each of which is unknown by orders of magnitude. The first is abiogenesis, the probability that life arises at all on a world with the right architectural conditions and chemistry. We have one example, and we do not know whether that example is typical or extraordinary. The second bottleneck is the transition from simple to complex life, specifically the emergence of eukaryotic cells from prokaryotic ancestors. On Earth, this transition appears to have occurred perhaps only once across the entire history of the biosphere, after roughly 2 billion years of purely microbial life. Whether eukaryotes are a universal feature of long-lived biospheres or a singular accident is one of the deepest open questions in modern biology. The third bottleneck is the development of recognizable intelligence. Complex multicellular life has existed for roughly 600 million years, but human-level cognition, with language and cumulative cultural learning, has existed for perhaps a few 100,000. The fourth is the emergence of communicative technology, which on Earth has existed for roughly 1 century of radio frequency transmission. Each bottleneck multiplied against the others produces a final figure that spans from 1 in a billion to nearly 1 in 1, depending on which assumptions you bring to the calculation. The rare Earth hypothesis represents the pessimistic end of that probability range. and it deserves to be held honestly rather than dismissed. The argument is that the full architectural stack required for long-lived complex life is far narrower than the habitable zone definition implies. A host star of the right spectral type, neither too active nor too short-lived. A galactic location inside the habitable annulus, away from the supernova rate and gamma ray burst frequency of the inner galaxy. A protective outer solar system architecture with large planets shepherding debris away from the inner system across billions of years. A planet of the right size with a strong magnetic field, with plate tectonics, with a large stabilizing moon, with a stable rotational axis, with persistent surface oceans, with a low long-term impact rate, with billions of years of continuous habitability. Each individual condition is plausible on its own. The conjunction of all of them simultaneously and persistently may be genuinely rare. The counterargument is that we are reasoning from a single example, and the single example we have produced life, complexity, intelligence, and technology in sequence. The Copernican position holds that Earth is probably not extraordinarily special among habitable worlds. The honest current position is that both views are scientifically respectable, and the available evidence does not yet distinguish between them. The Great Filter concept maps onto this uncertainty in a way that carries genuine weight. Somewhere along the chain from a habitable world to a detectable civilization, there's likely at least one step so improbable that it explains the silence we observe across the galaxy. If the filter is behind us, if the eukaryotic transition or the emergence of multicellularity or the development of intelligence represents that bottleneck, then we have already passed through the narrowest gate and the rest of the chain may be relatively traversable. If the filter is ahead of us, if the long-term survival of technological civilizations is the bottleneck, then we may be approaching the most dangerous threshold rather than looking back at it. Several decades of radio searches, optical laser surveys, and waste heat infrared scans have produced no confirmed evidence of any technological civilization anywhere in the galaxy. The silence is real, and it carries information, though the information is ambiguous. It may mean we are alone. It may mean civilizations are quiet by design, or that we are too early, with most of them still forming in the future. It may mean we're listening at the wrong frequencies or searching the wrong portions of the sky. The silence is consistent with all of these explanations simultaneously, and it does not yet distinguish between them. The gap between the enormous habitable count and the empty inhabited catalog is the size of everything we do not yet know. The next 2 decades represent the first period in human history when the instruments pointed at this question are genuinely capable of beginning to answer it. The James Webb Space Telescope, operational since mid-2022, has already produced atmospheric characterizations of the most observationally accessible habitable zone candidates, and will continue refining those measurements through the late 2020s. The Roman Space Telescope, scheduled for launch in the late 2020s, will conduct a wide-area microlensing survey expected to discover thousands of new exoplanets, including cold and free-floating worlds that transit surveys cannot reach. The A-to-Earth value, currently bracketed between 0.1 and 0.8, should narrow considerably once Roman's population statistics are available. 3 extremely large ground-based telescopes are approaching completion. The Extremely Large Telescope in Chile with its 39-meter primary mirror, the Giant Magellan Telescope also in Chile with its array of 7 8-meter mirrors, and the 30-meter telescope in Hawaii. All 3 are expected to reach scientific operations in the late 2020s or early 2030s, and all 3 are capable of directly imaging planets around the nearest stars and reading their atmospheric compositions through high-resolution spectroscopy. If Proxima b has a thin remnant atmosphere, these instruments should be able to characterize it. If any of the nearest habitable zone candidates carry biosignature chemistry in their skies, the extremely large telescopes will have a genuine chance of detecting it. The Habitable Worlds Observatory is the instrument specifically designed to answer the biosignature question at the population level. Currently in concept development at NASA, with a projected launch in the early to middle 2040s. Its central design goal is to directly image at least 25 Earth analog planets around nearby, Sun-like stars, and obtain spectroscopic atmospheric characterizations of each. It is the direct successor to Hubble and Webb in the flagship mission lineage, and its scientific objective is the most consequential one the field has ever formally adopted. If the mission flies on schedule and meets its specifications, the question of whether any of the nearest 25 Sun-like stars hosts a planet with chemical signatures of life will be substantially answered within roughly 20 years from now. The Plato mission from the European Space Agency, scheduled for launch in the late 2020s, will conduct long-duration transit surveys of bright Sun-like stars to find Earth analog planets with orbital periods of months to years, extending the catalog into the period range that Kepler and TESS could not fully reach. Ground-based extreme precision radial velocity programs, including ESPRESSO at the Very Large Telescope, MAROON-X at Gemini North, and X-BRAZE at the Lowell Discovery Telescope, are pushing measurement sensitivity toward the threshold needed to detect Earth-mass planets around Sun-like stars directly. The Parker Solar Probe, the fastest spacecraft ever launched, travels at approximately 150 kilometers per second, a speed that would require roughly 8,500 years to reach Proxima b. The answers we are waiting for will come from spectroscopy across light years, not from instruments at the worlds themselves, and they will come piece by piece across the next several decades. The honest answer to the question this catalog was built around is a layered one, and the layers do not all resolve in the same direction. We know with certainty of exactly one inhabited world, and that world is the one the question is being asked from. We have plausible candidates in the dozens. Kepler 22b at 620 light-years, perhaps a global ocean world beneath an atmosphere we cannot yet describe. Kepler 452b at roughly 1,400 light-years, perhaps an older cousin to Earth, or perhaps already crossing into runaway greenhouse from the inside. Proxima Centauri b at 24 light-years, the nearest known potentially habitable world, perhaps a thin atmosphere Terminator planet, or perhaps stripped bare. The 7 Earth-sized worlds of TRAPPIST, 1 at 39. 6 light-years, orbiting a star that will burn for trillions of years, their atmospheric fate still being measured. K2-18b at 124 light-years, a hydrogen-skied ocean candidate with the faint chemistry of methane and carbon dioxide and the contested whisper of dimethyl sulfide in its spectrum. We have statistical estimates placing the habitable count in the galaxy somewhere between several billion and several hundred billion, and across the observable universe in quantities that exceed the capacity of language to convey. What we do not know is the most important thing. How many of those worlds are actually inhabited? What the silence of our radio telescopes is telling us, whether biogenesis is common or vanishingly rare, and whether the conditional probability chain from habitable to communicative is wide enough at each step to populate the galaxy with neighbors, or narrow enough at some single bottleneck to leave us effectively alone. The first confirmed biosignature on any exoplanet, if it arrives, will be a turning point as significant as the first confirmed exoplanet itself in the mid-1990s, and the instruments now being built are the first ones in human history genuinely capable of producing it. Somewhere in the Cygnus constellation tonight, a possibly oceanic world is tracing its 290-day orbit around a star slightly cooler than ours, its surface unseen and perhaps unseeable beneath a global ocean we cannot describe. Somewhere in Centaurus, a small rocky world is locked into permanent day and permanent night around the nearest star to us, its atmosphere either thin and marginal or long since gone. The answer approaching on the timeline of the next large telescope. Somewhere in Aquarius, 7 Earth-sized worlds are resonating in their ancient chain around a dim red ember that will still be burning long after every star like our sun has exhausted itself and gone quiet. Somewhere in Leo, a hydrogen-wrapped ocean planet is completing another circuit of its small red host, its atmosphere carrying the chemical fingerprints of something